Before the world was explained, it was felt. Before equations were written, light was already traveling, quietly, faithfully, in a straight, unbroken prayer. But then, it met something. A boundary, a surface, a different way of being. And in that moment, it did not shatter. It bent, softly, precisely, inevitably, as if the universe whispered, to exist, is to adapt. A pencil appears broken in water, but it is not the pencil that changed. It is the path of light, learning a new language. And maybe, every time we enter a new world, a new culture, a new truth, we too are refracted, not lost, not wrong, just seen through a different medium. Welcome to Shellz Diary, where light does not just travel, it transforms. Where numbers are not merely counted, they are remembered. Here, steam shapes the world you can touch, the visible, the measurable, the precise. And slope reveals the world within, the felt, the hidden, the understood without words. A space where science softens into poetry, and poetry finds its structure in science. So if you've ever sensed that reality is more than what appears, that truth bends, shifts, and unfolds depending on how you look, then you are exactly where you need to be. Welcome home. Today we will discuss Snell's law of refraction, not just as a formula, but as a thread woven through history, science, and the rise of our modern world. Long before modern equations, during the Islamic Golden Age, knowledge was not divided into subjects. At centers like the House of Wisdom, religion, philosophy, mathematics, astronomy, and what we now call science were studied together, as one continuous search for truth. In this environment of unified knowledge, scholars turned their attention to light. Among them was Ibn Sahl, who, around 984 CE, described how light bends when it passes from one medium to another. He did not use modern symbols, but through geometry, lines and angles, he captured a precise relationship between the angles of incidence and refraction. Centuries later, this same relationship would be written as,
observe the symmetry in these intersections. Yes, and let us test further.
Snell's law, named after Willibrord Snellius, even though the principle itself had already been discovered. Later, Ibn al-Haytham expanded the study of optics further, connecting light, vision, and experimental method, laying the groundwork for modern scientific thinking. Now let's understand the physics clearly. Snell's law describes how light behaves when it crosses a boundary between two media. The key idea is this: light changes speed when it enters a new medium. This change in speed is described by the refractive index, where c is the speed of light in vacuum, and v is the speed of light in the medium. When light enters a medium with a higher refractive index, it slows down. And when its speed changes, its direction changes. This bending is called refraction. Importantly, the frequency of the light remains constant. The wavelength changes. The speed changes depending on the medium. All of these changes are connected through the wave relation, v equals f lambda. Snell's law ties these ideas together and tells us exactly how the angles change. Now here is where history meets modern life. Today, this same principle is the foundation of fiber optics, the technology behind high-speed internet. Fiber optic cables use a core with a higher refractive index, surrounded by a cladding with a lower refractive index. When light enters the fiber at the correct angle, it undergoes total internal reflection, bouncing repeatedly inside the core instead of escaping. This allows light to travel vast distances with very little loss of signal. And this is how data moves across the world. Every video you stream, every message you send, every signal in the global network, travels as pulses of light guided by the very same law discovered centuries ago. So Snell's law is not just an equation. It is a bridge, from the geometric insights of Ibn Sahl, to the golden age of unified knowledge, to the invisible infrastructure of our modern world. A single bending of light, that now carries the voice of humanity across the planet. Today we explore a subtle but important truth, one that connects light, sound, and the idea of refraction under a single principle. Because Snell's law is not exclusive to light, it applies to waves, and that includes both electromagnetic waves like light, and mechanical waves like sound. When any wave crosses from one medium to another, its speed changes, and because of that, its direction changes. This is the essence of Snell's law. It describes how the angle of a wave adjusts in response to a change in medium. Now here is the key distinction you must hold carefully. For light, when it enters a medium with a higher refractive index, its speed decreases, and it bends toward the normal. When it moves into a lower refractive index, its speed increases, and it bends away from the normal. For sound, the same principle applies, but the behavior is often counterintuitive. Sound is a mechanical wave. It depends on particles to transmit energy. In a medium like water or solid materials, where particles are closely packed and more strongly connected, sound actually travels faster. So when sound moves between media with different properties, its speed still changes, and because of that, it still bends. It still follows Snell's law, but the direction of bending depends on how the speed changes in that specific medium. So the law remains the same: change in medium, change in speed, change in direction. But the behavior differs because light and sound are different types of waves. They respond differently to the same medium, and their speeds increase or decrease under different conditions. Light slows down in denser optical media. Sound speeds up in denser mechanical media. Yet both still obey the same fundamental geometry of refraction. Both still bend. Both still follow the angle relationship. Both still carry energy across boundaries. This is the deeper unity of physics. Different waves, different behaviors, but one underlying law governing them all. Snell's law is not just about light. It is about how waves respond to change. And whether it is light bending toward the normal, or sound bending through a denser world, the message is the same: when the medium changes, the path must change. Today we are standing at the edge of something fascinating, a boundary between two mediums. Because this is where waves decide their fate. We know that when light or sound moves from one medium into another, its speed changes and it bends. That bending is called refraction. But what happens when we push that bending to its limit? Let's imagine light traveling inside water or glass, a denser medium. As it tries to exit into air, it slows down differently, and it bends away from the normal. Now here's the key moment. As we increase the angle at which the wave hits the surface, the bending becomes stronger, until something very special happens. The refracted ray reaches an angle of 90 degrees, it travels along the boundary itself. This angle is called the critical angle. At this exact point, refraction is no longer entering the new medium in the usual way, the wave is just skimming along the surface. And now, if we increase the angle even more, something powerful happens. Refraction stops. Completely. Instead of passing into the second medium, the wave is reflected back into the original medium. This is called total internal reflection. No transmission, no bending into the outside. Only reflection, and the conditions are very specific. The wave must move from a denser medium to a rarer medium, and the angle of incidence must be greater than the critical angle. When both conditions are met, the wave cannot escape. It stays inside. It reflects again and again. And this is not just theory. This is the principle behind fiber optics. Inside tiny glass fibers, light is trapped using total internal reflection. It bounces along the core, carrying information over long distances with almost no loss. That is how data travels, how the internet moves, how the digital world stays connected. So what we learn here is deeper than just physics. At the boundary, there is a choice. Below the critical angle, the wave bends and continues. At the critical angle, it travels along the edge. Beyond the critical angle, it turns inward and reflects. And maybe that's the quiet message of this law. Sometimes, when the path ahead changes, you don't go forward. You bend, you reflect, you continue, from within. And so we arrive, at the end of the bend. Light has traveled, angles have spoken, and waves have revealed a truth older than equations, that nothing moves through this world without changing, without adjusting, without learning the shape of its path. Because every boundary is a question, and every wave, light, sound, thought, or feeling, answers in its own language. Sometimes it bends, sometimes it reflects, sometimes it cannot cross at all, but it never stops moving. So maybe the real Snell's law is not just written in physics, but in life itself. When you enter a new world, you will not remain the same. You will slow down, you will speed up, you will stretch, and you will compress. But something within you, your frequency, your essence, remains unchanged. Unbroken, unwritten, unbent, that is the quiet constant moving through every medium. So as we close this chapter of Shellz' diary, remember this: not all truth is straight. Some truths are found only in the bend. Stay curious, stay aware, stay in motion, and wherever you go, let yourself refract into something even more luminous. Until next time, take care and bye.